In this video, we're going to take a couple of the relationships from the previous video and sort of combine them to simplify some things. And so ultimately, we're going to be looking at something called the dielectric constant and also discussing briefly our dielectric strength and some non-ideal things that can go on with our dielectrics. So from the previous video, we had these two expressions here. And so what we want to do now is just combine those, and we can say that our D is equal to epsilon naught times 1 plus that chi E, which is our susceptibility, times our electric field. And so let's go ahead and say we'll introduce a new variable, and let's make this epsilon naught times epsilon r. And so I'll define this explicitly here in a little bit, but that epsilon r is going to be our relative permittivity of the dielectric. And so, of course, we can see from our previous video that chi relates our polarization to the electric field, so our relative permittivity is related to the polarization or the potential for polarization of our dielectric material. So in general then, we can say that our D, our electric flux density, is just equal to epsilon times E. So notice there's no subscript on that epsilon, and that epsilon then is just equal to epsilon naught times epsilon r. So our permittivity of free space times our relative permittivity. And so again, just to write this relationship explicitly, we have that relative permittivity is equal to 1 plus our susceptibility, chi sub E, which is equal to epsilon divided by epsilon naught. So we have a few different ways to approach that. And so let me define these things sort of explicitly here. So we've already talked about this, we've talked about our permittivity of free space, but this is our epsilon with no subscript is just going to be the permittivity of the dielectric. And so it's going to have dimensions of farads per meter. Our epsilon naught is just going to be the permittivity of free space. So let's just copy that. That might be longer than writing it, but oh well. So our epsilon naught is permittivity of free space or of vacuum. And so that also is going to have dimensions of farads per meter. And now our epsilon r, our new term here, is our relative permittivity. So relative permittivity. So we're basically saying, what is the permittivity compared to vacuum, compared to free space? And we'll also see this called our dielectric constant. So dielectric constant. And unlike the other two, so based on sort of this relationship here, we can see that if epsilon and epsilon naught both have units of farads per meter, then we expect our relative permittivity to be dimensionless. Dimensionless. Let's get an extra S in there. And so if you look in table B2 in the textbook, you can see some common low frequency or static values for our relative permittivity for common dielectric materials. So one thing that's worth mentioning too is in this text we're only going to consider ideal dielectrics. So in this text, in this class, also in the textbook though, only ideal dielectrics are going to be considered. But of course that's not going to be the case if we're working with dielectrics in the real world, whether it's with capacitors or some other relevant application, we're going to have real dielectrics. And so a couple things we want to talk about is dielectric breakdown and dielectric strength. So dielectric breakdown is when our E field is getting strong enough that it's starting to pull our electrons out of that molecule or out of that lattice. So strong enough to remove electrons from molecules / lattice of the dielectric material. And so at that point we now have free electrons and we basically have conduction. In practice, what's going to happen is you're going to destroy the dielectric, you're going to have a brief surge of current, and then the device isn't going to work after that. So related to this dielectric breakdown, we can define something called dielectric strength, which is basically just how much electric field or how much voltage can a dielectric handle? So dielectric strength is basically just our maximum E that a dielectric can handle without breaking down. All right. And so there are a lot of things that this depends on. So this can range from things like temperature, humidity, are some pretty obvious ones that it's going to depend on. How long the E is applied, so time of our electric field applied. So in some cases, you'll see ratings for instantaneous voltage, or maybe it's a voltage over a certain time. So that's definitely something we want to consider. Another thing that also affects our dielectric strength is our dielectric growth process. So we've talked about this a little bit in other classes in terms of dielectric growth, or maybe we've just touched on it briefly. But basically, if we're using a wet process or a dry process, that can affect our dielectric strength. And again, there's a whole lot of things that can affect that, but ultimately in this course, we're just going to be focusing on our ideal dielectrics and sort of working with the basics.